let's get started. So first of all, I think there was sorry, there was a typo in the program set, and yes, and then so it turns out there will be no homework this week and next week, so that you guys can have enough time to prepare for the final presentations, and then so yes, and then because of the typo, if you need more time, you can submit the homework next week if you want.
Some of us haven't got back for the emails regarding the projects.
Right. So now, yes. So I don't. Not everyone is here, I guess, today. But so right now, right. So I think there are eight students. No, 7 students.
2 of them are out of town today.
Out?
Yeah.
Oh, okay.
I mean, they're not here today.
Oh, yeah, sure. And then, so I and Daniel will be splitting who will, take care of whose project and so on. And then, so is it you haven't heard back from anyone, or?
Yeah.
So what's your name?
Dilakar.
So you are doing surface code decoding, right?
Yeah.
Oh, yeah.
We discussed a little bit in class, but like I sent a list of papers.
Sure. And then, you wanna know like if it's a good idea to work on these things and so on?
I've already started working, so hopefully that's a good idea.
Oh, okay. So, right, yes. So, yes, I'm supposed to take care of your project, so I will, or maybe we can chat during the break, and then do you know if any other people?
I got a very confusing response from Daniel.
You're doing turbo codes?
Yeah, turbo codes. Yeah.
Yes.
And he just said okay, and then sent me a reference to another type of paper. So I was wondering if I could also have advice on like papers related to turbo codes.
Papers of what?
So I mentioned in my email curiosity about polar codes, and got references for polar codes and none for turbo codes. So I was wondering we're looking for references for that. Like I've mostly just used like the first Google result and have started there.
Oh yeah. Also, Daniel didn't give you any list of papers.
Not for codes.
Maybe you can send him an email.
All right.
And then right. So anyway, okay. Right. So basically, if you are unsure about which papers you want to cover and so on, then just let us know. And I guess it would be a good idea to let you know that who will be taking care of who and so on. Okay, but anyway, so I'll send out an email later. Okay, so right. So today's topic is about so 2 things. First is about the so-called Clifford hierarchy. That is So first topic is Clifford hierarchy, and second one is a subsystem code. So as you know that the Clifford gates are something easier to implement with high precision, but the non-Clifford gates are not that easy to implement. But there is an interesting kind of hierarchy of gates you can implement on them. So this will be the central topic. So Clifford hierarchy consists of like mth level, where m is some integers starting from 0 and 1, 2, 3, 4, 5, and so on. And then it's just a bunch of sets of unitary operators. And at 0th level, we only have something very trivial, such as identity operator or identity times some phase. So basically U1 phases. So this is a very trivial gate, which is easy to implement, or you basically don't need to do anything. And
what's the mth level? Is that unitary that acts on m qubits?
Sorry?
What's the mth level? Is that a unitary that acts on m qubits?
Oh, mth level? So I'm going to define it.
Right.
Yeah. So then, so first level, so I will define it precisely, but let me just give you the idea of how these things would look like in actual system. And then we will be interested in a system with n qubits. We are thinking about a set of all the unitary operators acting on these n qubits. And this Clifford hierarchy is just subset of these unitary operators. And the first level is a bunch of Pauli operators, like x, y, z, or their tensor product. So it's slightly more difficult to implement than zeroth level, but not that much. And the second level consists of the Clifford gate. So by Clifford gate, which is, well, example is like C node, control Z, or S gate, this kind of gate. And just to recap, the Clifford gate is an operator which maps some Pauli operator P into some Pauli operator Q. So the point is this P and Q could be different. So it's a kind of permutations of Pauli operators. Well, up to some phases. Phases are not that important at this point. Okay, then finally there is a third level gate, fourth level gate, and so on. And starting from this third level gate, we have some non-Clifford gates. And then, and then third level gate actually contains things like T gate and 3-qubit control Z gate, and so on. And then in the fourth level, you have some more complicated gates. So roughly speaking, the picture is that you have a set of all the unitary operators. This is all unitary. Then you have first level, which is Pauli. Second level, that is Clifford. Third level consists of some of the non-Clifford gate, like CCZ and so on. It keeps going. So this is a hierarchy of a set of the unitary operators. Now I'm going to use these notations C0, C1, C2, and so on to denote the set of these operators. Now, I didn't give any definition of how to construct this hierarchy, but I just illustrated the fact that this set Cn, Cm is sort of increasing as M becomes bigger and bigger. But now let me give you a formal definition of the Clifford hierarchy. All right, so the formal definition, it is convenient to use something called commutator. So let A and B be some unitary operator. Then commutator K between A and B will be defined as the following. A B, A dagger, B dagger. Okay. So the reason why we call it commutator is because if AB commute, then it's just an identity operator because this ordering does not matter. Then you can bring A dagger to A and cancel. But if they are not commuting, then you get some non-trivial operator or something other than identity operator. Now with this commutator, so maybe I can give one non-trivial example, that is commutator between x and z is xz, xz. Well, you don't need dagger because it's Hermitian. And this is minus I. That's just two examples. Okay, now given these commutators, we can define the Clifford hierarchy in the following way. So it's defined in a hierarchical manner. So Cm plus 1 is defined as bunch of unitary operator U, so that for all P Pauli operator, commutator is in the one lower level of the hierarchy. Okay. So you pick, let's say, one operator from m plus 1th level, and you just commute it with Pauli operator, and you get one level lower, a bit inside in this diagram. So that is the definition of the commutator and the Clifford hierarchy. Okay. Is there any? I'm going to look at several examples, but is there any question about this definition?
I also had some questions about the hierarchy above it.
Sorry?
I had some questions about the hierarchy above it. On the board above, you have something called a Clifford hierarchy, and I had some questions about that.
Yeah.
So am I right in thinking that you need as far up as the third level for universality, but you don't need past that?
So sorry, I need third level for the universality?
Yeah, I'm asking, universal set for quantum computing. Now the furthest one up there that I see the first appearance of is the T-gate at third level. Right, so am I right in thinking you only need to go up to the third level to achieve universality? Right, so
right. I mean, assuming that Clifford is free.
Right.
Yes, that is the case.
I mean, otherwise, if you only go up to second level, you're presumably still subject to Gottesman-PI and its related.
Oh yeah, it is.
Thing, so it's not actually universal. So you need to set this third level is necessary as well.
Right. But actually, important thing here is C0, C1, C2, C3, C4. Everything is a set. It's not a group. I mean, if it was a group, then let's say C3. So by definition, Cm plus 1 is bigger than Cm. But suppose this is a, so let me write. Larger than 2. The reason is the following. If it was a group, let's say a group, then the problem is that well, C3 contains full Clifford group. That is C2, basically. And T-gate, which means that the C3 is unitary group itself. Well, it's a dense cover of the unitary group. But it's not the case in the sense that there are gates which do not belong to the third level, and so on. So.
Right, and yet they're not decomposable in terms of smaller gates.
Decomposable means?
Well, universality means you can break any larger gate down to a sequence of the smaller gates.
Sure.
Right, so how can you have something that's only occurs higher than the third level? I can decompose it.
Oh, what does it mean by decompose? There's no way of exactly representing it.
Right, so you're inviting a small print in.
So as you see, this defines the set of operators, right? And then, so what is the question?
Okay, well, one of the things that you try and do with a quantum computer is you make a set of universal gates so that you can do your quantum computing. Now, there's a small print in Solovay-Kitaev which says that these are actually a dense cover.
Yeah.
So I'm asking, are you invoking that when you say that there are gates which are fourth level which do not occur lower down?
No. No, it doesn't conflict with Solovay-Kitaev because Solovay-Kitaev has nothing to do with, because Solovay-Kitaev is just a bunch of, decomposition gates, right?
Right, but it's all about, if I want to do quantum computing, I need 2-qubit gates, but I don't need.
So right. So that's what I mean by it's not a group. If it is a group, then you are allowed to think about like decomposition from third level gate, because multiplication should be inside a group by definition. But this is not a set. So if you do some decomposition and then with third level gates, then the outcome could be in the higher level gate.
Right, so you're saying that there are things in the third level which are 2-qubit gates?
Sorry? There are two...
I'm sorry, what you're saying seems to flatly be internally inconsistent.
No. I'm saying like it is not a group. So you are not allowed to think about like...
universality theorems that underpin all of quantum computing, which make very strong statements about decomposing.
Yes, gates. Like decomposing means like you decompose one unitary operator into a product, right?
Right.
But by definition of group, it's not a group. So suppose that you have some gate, third level or fourth level, it doesn't matter. Let's say you are able to decompose it into this form. All of them are in the, this is a third level gate. Everything is third level gate. But this does not imply that, then you are saying like, this should be inside third level, but this is not the case. Because this is not a group.
The only way I can see out of the contradiction is that it's about what the domain that these different groups are acting on. So that if you have you're looking initially at a 3-qubit gauge, now you want to decompose it, but you still have to have your 2-qubit gates acting on each pair of 3-qubit gates. Whereas a Clifford hierarchy is restricted to acting on 2 qubits.
No, it's not like that. You can define Clifford hierarchy even with n equals 1, single qubit.
Right, but I'm talking about decomposability results. So if you restrict to 1 qubit, that problem becomes trivial.
Sure. The statement, all this statement applies to any number of n.
Right. You're saying you keep saying it's
the answer is pretty simple. Like C3 is not a group. That's it.
Yeah, but I'm not invoking its group properties. So that's irrelevant.
So what's the contradiction?
Well, there's a universality result which states that you can decompose any quantum circuit into a product of 2-qubit gates.
With some epsilon errors. Yes.
Right, with some epsilon errors which are handled.
Well, let's forget about it. Yes, suppose it's true.
Okay, so now there's the Gottesman-PI, which says that if you can only do Clifford gates, then that's not universal. You need an extra gate, which is the T gate.
Which or any non-Clifford gate is fine.
Right, okay, but once you have that T gate, you're now able to do universal computing.
Yeah.
Right. So why do you need a fourth level? Well, how can there be anything in the fourth level which cannot be expressed as a product of stuff in third level or below?
So what is the question? Is it more like why do we need to think about fourth level, fifth level?
Well, there's that for a start. If we restrict to that, that's enough to be a sharp question, I think.
Sure. For example, I haven't given you any examples, but if you want to know why we should think about higher level gate, then we can talk about it later in the lecture. But I mean, what you said doesn't contradict with any of these definitions, right?
Yeah, I'm just...
I mean, all you said is like, yeah, let's add T-gate and it is universal. Yes, that is true.
But for something like the control Z gate, that can be decomposed. I mean, that's what you mean by CCZ gate. Yeah, it's a control Z.
Okay. Control Z gate is a third level gate, and
Well, yeah, but isn't it decomposable?
Okay, let's keep moving because I think these things are actually covered partly in the program set, and I'm assuming like people are sort of exposed to these ideas previously, but maybe you are not.
Well, I don't know what universality is.
No. I'm talking about the program set.
Right.
So you haven't looked at. So I'll review it. So. Okay, so let's look at examples. So C1, I said that it is a set of Pauli operators. So let's see that it makes sense. So we are interested in a unitary operator whose commutator with Pauli operator is just a U1 phase, right? But you see that this set of Pauli operator is precisely this object, because if you have, then this is basically plus minus 1. So it's U1 phase. And of course, you can generalize this definition pretty easily for qubits, because qubit Pauli algebra has U1 phases too. But this tells you that C1 is basically Pauli. Okay, so let's go to the second level. That is a unitary, which where the commutant is the commutator is the Pauli group. So this was basically Pauli. And then so again commutator is given by this object, right? So this must be equals to some Pauli operator up to some U1 phase. This means that U dagger is just Q times P. So this is another Pauli operator. This means that Pauli operator transforms to another Pauli operator. So C2 must be preferred. Okay. Now, these are very easy examples to see because C1, C2 are group. But now let us look at a few examples. And that is, so let me begin with some family of single qubit gate, which is called RM. So this is a single qubit operator, which is diagonal, and it's a phase gate. Okay, it's defined like this, so maybe I can explicitly write it down. Right. Okay, so this is a definition. So the claim is that Rm belongs to yes, this direction. Is in the mth level of the gate, and it's actually outside of the m-1. So it's a non-trivial gate in the mth level. So to see this, well, let's look at one by one. R0 is an identity operator. R1 is Pauli Z operator. R2 is S operator. R3 is a T operator, and so on. It keeps going. This is C0, C1, C2. Now, to prove this statement, what we should look at is actually pretty simple. We are going to compute the commutator between Pauli X and this phase operator Rm. And more explicitly, this is subject. Okay, well, this is just multiplication of matrices, and then I guess I put this as a problem set, in a problem set, so I guess many of you will know how to do it. It turns out this is proportional to Rm-1 with some phase. So this means that by commuting Rm with X, you get one level lower. And then you can inductively, recursively prove that this implies that. So as you can see, higher level gate, sort of in this example, higher level gate corresponds to more fine-tuned rotations. When M is very big, then you can do a very tiny rotation angle. Okay. And another example is the control Z gate. Well, more precisely, this is a multi-qubit generalization of the control Z gate. So let me write M qubit control Z gate as follows. And then let me give you a definition. So this is the how it acts. This is a diagonal operator, and act in the following way. Well, this is just a product. Okay. So what basically this does, or why we call it control Z gate, is because, well, in this circuit diagram, you could draw it like okay. And these dots can be viewed as control qubits, and we apply Z operator only when we apply Z on mth qubit. So this is what we mean by multi-qubit control Z gate. And well, even though we are using these qubits as a control, but you can see that this construction actually is symmetric. So basically you gain -1 phase only when everything is 1. Other than that, you don't get any phase. Now, we claim that this this gate belongs to mth level. So sorry, I'm using kind of similar notations, but control and Clifford, but I think it's understandable from the context. So M qubit m-qubit control Z gate is inside the mth level of the hierarchy. And to see this, you can actually compute a commutator. So not then you see that it is a multi-qubit gate with 1 qubit lower. So more explicitly, you can see this by this circuit. So this is basically XM. You do multi-qubit control Z. So this is a commutator. And if you just directly compute this object for each basis state, you get that this looks like this. Where this is n-1 qubit. So then by doing this hierarchically, actually, so what actually you need to compute is a sequential So what you need to compute is like this sequential commutator. Okay. Then you can show that, so at the end of the day, actually, this part, n-1 part becomes 0, and then you get just Pauli operator. So that's how you can prove this. All right, so hopefully you can gain some intuitions from this. We have already run several examples of quantum error correcting codes where these gates are transversal. First, read mirror code. This is defined with 2 to the n+1 minus 1 qubit. So I'm going to use NKD notation. N equals 1 qubit, and then distance is 3. This read mirror code has RM gate, which is transversal. Okay. And yes, m equals to 3 corresponds to the 15 qubit code. There's T gate. But another interesting example is it's discussed in the problem set, but some quantum codes defined on a hypercube. This one has the following parameter: 2 to the m. It encodes, how many it encodes? Yes, m. So these parameters. And for these codes, this multi-qubit gate is transversal. And it turns out that these two types of code are some can be obtained. M-dimensional topological color code with some appropriate boundaries. Appropriate choice of boundaries. Okay, so this is like a very brief introduction to the Clifford hierarchy. Good. So now, since we have defined the hierarchy and sort of, so we sort of see that the gates from the higher level are much more difficult to implement because on one hand, it consists of a very tiny fine-tuned rotations, which are definitely something we want to implement with high precision. So, and also, the other hand, we have multiple control Z gate, which creates a multipartite entangled state. So for these reasons, we sort of expect that the gates from the higher level would be much more difficult to implement. So let me make this intuition more precise. So now we are interested in transversal code, transversal gate in stabilizer code. And then now given a quantum error correcting code, let's say a stabilizer code, can we implement a gate from 3rd level, 5th level, 10th level, and so on? That's the kind of the question we want to address. And let me introduce one very powerful lemma, which says the following. So let's consider some n-qubit gate, n-qubit stabilizer code. So it's n-qubit, and then now, so this is the entire space of qubits. So its qubits are sitting like this with their own stabilizer generators. We are going to split the system into n+1 part. So let me call this part A0, A1, so on, and AM. So there are n+1 subsystems. Okay. Now, let us consider a logical operator, L. So this is some logical operator. And we assume that this is transversal logical operator. Actually, it's much more than the ordinary transversal operator, but so it is just important to have A1. So you have n+1 regions, and it's important that this has a tensor product structure over n+1 regions. I mean, you can assume just ordinary transversal gate like bunch of S or 10 T or and so on, but in practice, this is all we need. And a new choke. Okay, now if this is the case, then oh no, I didn't say any conditions for this lemma. So we consider the any arbitrary non-trivial transversal logical operator. Let's assume that this AJ does not support any logical operator. By which I mean that if we count the number of the non-trivial logical operator, Pauli logical operator on each subsystem, subregion, then it is 0. Okay. This is assumption of the lemma. Then this assumption, it turns out leads to the following result, that is L should be in nth level of the hierarchy. Okay. Now, this lemma, you need to use it in a clever way. So, for one thing, this assumption, for example, you can think about, yes?
Oh, sorry, I just want to verify, based on the picture, we're dealing with like a topological stabilizer code?
Or anything, so any stabilizer code.
So then what does GAJ mean if we have a non-topological code?
So what do you mean by non-topological?
Like, I don't know if it's just a string or something.
Oh, it's just stabilizer code in the sense that you can imagine n-qubit arbitrary stabilizer code with stabilizer generators. I mean, you don't need to assume any geometry. So this is just a stabilizer code.
Okay.
And then you split n-qubit into n+1 subsystems as you want. So it's an arbitrary splitting.
Okay.
So any splitting is fine. So let me give you some intuition about this lemma. And let me explain why I said we need to be clever to use this lemma in a meaningful way. Because, for example, let's say like there are m qubits, so I can split the system into n regions. That is, each region contains single qubit. This is kind of a trivial example. Yeah, you know. Then you see that, well, in a normal quantum error correcting code with error correcting properties, a logical operator must have some high weight. Well, at least it's not one body operator. This means that all these regions do not support any logical operator. Right? For all, so this is M subsystems. Then this lemma says that, okay, what you can do is contained in nth level of the for the hierarchy. Okay, but the problem is n is a very, very big number, so this restriction doesn't tell me much. So like, it's a huge, huge region and huge, huge set. So in order for this lemma to be more successful, you want to make this A0 and A1, A2 and so on as big as possible so that this number m is very small. And then that's what I mean by we need to be clever enough to use this lemma in a meaningful way. But I'm gonna tell you one nice example of such an application. But for now, let me just give you the proof of this lemma. Yes?
So there you have L's in Cm and L's in Cn.
Oh, right. Sorry. So this is a statement of the lemma. Okay. Now let's use this lemma to this stabilizer code by splitting the entire system into m subsystems. So this must be actually n minus one. I mean, this says that you are given a stabilizer code and then you can consider any partitions. So as a trivial partition, I claim that first qubit belongs to A0, second qubit belongs to A1. So just bunch of single qubit partitioning.
So what are these subsystems though? Right, what's a subsystem?
Subsystem is just a list of qubits. So given a qubits, you are able to put it in any regions. It's important that they contain at least one qubit. So one trivial example is that each region contains only a single qubit. Then I have n subsystems. And then single qubit cannot support any logical operator, right? Because as you see that in the toric code or in the 5-qubit code or in all these examples, logical operators are like 3-body or n-body. It's a very weak operator. If it's 1-body, then you can easily kill the information. So this implies that there is no logical operator supported on each subregion, subsystems. So this is true. So this partitioning satisfies the requirement of the lemma. Then the lemma tells me that, okay, the transversal gate in this system is contained in a level of the n-minus level of the Clifford hierarchy. Okay, that's the theorem, but that's what implied by the lemma. But now I'm saying that this lemma, well, this result doesn't tell me anything because n is a very, very big number, and then you can go pretty far and contains a lot of gate. So in order for this lemma to be meaningful, to see some useful restriction on logical gates, you want to make this number of partitions as small as possible while satisfying this condition. That is message in this example. Yes?
So where is the logical qubit or logical qubits plural in your n subsystems?
Where is the logical qubit?
Yeah, I mean, if you want to divide a system up like that, that's what...
So, right. So I'm implicitly assuming that this is a quantum error correcting code in the sense that the distance is not equals to 1. D is larger than 1, at least 2. Then this implies
so
that...
None of those subsystems corresponds to the logical qubit then?
Mm-hmm.
Right, because I'm thinking in terms of, you know, standard direct sum decomposition that you do if you want to find a subsystem as opposed to a subspace. Right, you can start off with a tensor product of a bunch of qubits, but your direct sum decomposition doesn't necessarily correspond to any qubits.
I mean, sure, but I mean, we don't need to think about any direct sum decompositions or so on. We are given a Hilbert space, which are just a direct product of the qubits, and we define stabilizer code with respect to these qubits. This defines the decomposition of Hilbert space, and you define the stabilizer code. And then the point is that this stabilizer code is a quantum error correcting code, which has the ability to detect single qubit error, implies this, right?
Okay, I think we may have a jargon problem here. Because I was taught that if it's a stabilizer code, it corresponds to a noiseless subspace. Whereas if you have a subsystem code, that implies you've got some kind of direct sum decomposition.
I mean, I haven't talked about subsystem code yet, right?
Okay, but you're specifically...
So you shouldn't think about, I didn't say. Okay.
Right, okay, because I mean, you're talking about subsystems and then you switch to talking about what appears to be a subspace code.
So, right, I mean, I haven't talked about anything about subsystem codes. I think, right, so...
Later, right, okay.
And then when you have subsystem code, actually there is a version of the lemma. Mm-hmm. This applies to subsystem quantum error correcting code. But, well, I guess we should look at stabilizer code first, right? It's much easier. Okay, so the game is like we want to split the system into some regions, some subsystems, so that all local regions do not support any logical operators. But first, let me prove this this lemma. Well, proof is pretty easy, but well, proof proceeds by induction, but I mean, writing down the induction step formally is just a bit stupid, so I will just tell you some intuitions. So first of all, we have this relation that is a logical operator on A subsystem and its complement. If you add up all the number of independent logical operators, then it's always equals to 2k. Now, by assumption, we know that AJ does not support any logical operator. This implies that all the logical operators can be supported on its complement. Okay. It's just some simple fact. Now, what we need to show is the following. Suppose that you have some transversal logical operator L, which is supported on S+1 regions. Then L belongs to level S. Okay. And then because this is an induction, so you want to assume it for S and you want to prove it that this applies to S+1 and so on. But the induction step can be done by the following observation. So now we have this just decomposition of Hilbert space. So there's a bunch of qubits. I'm just drawing the situation with these boxes. Now, let's assume that L is a transversal operator, which is supported to S+1 region. So let's write like L0, L1, LS. And for other region, it's just an identity operator. Okay. That's what we mean by supported S+1 region. Now, because of this property, this cleaning property, if we have some, so this is a Pauli logical operator, then we know that it can be supported on complement of AJ. So let's do this. Okay, so it's supported on all the regions except A0. Now you compute the commutator L and the P bar. So this is a logical Pauli operator, and this is your logical operator. And if you compute the commutator, then so you may get something here, something here, something here, but this is identity. This is identity. So the point is that the commutator with respect to identity operator is always just identity operator, because identity commute with everything. same here. So now the point here is that this commutator is defined on S regions. And it has a transversal form. So this each part is K L1 P1. This is K L2 P2. And so. Now, because we want to use an induction, so the point is that we know that this B should belong to C S minus 1. This implies that L should be inside S level. And you can use this argument here recursively, then you can prove this lemma. That is, you can basically put S equals to M. That's what you need to do. Okay. All right. Any question? Is it good or hopefully? Is this? All right. Okay, so now we have this nice lemma. So let me tell you a few nice application. So first is there some bound on transversal gate. For D-dimensional code. So you think about a family of code which is defined on a D-dimensional hypercubic lattice. And then let's ask what kind of transversal gate can be applied to this system. Now, first of all, let's assume that this code is non-trivial, by which I mean the following. The distance d is not constant. So d is something growing as the system size goes to infinity. Okay? And this is definitely needed in order for the system to have a non-trivial threshold. Okay. So I'm just saying like the code is actually working as a code. You don't want to have some trivial code where you encode quantum information into each qubit. That's pretty trivial. And you can do everything transversally. Now, under this assumption, it turns out that the transversal gate is restricted to this level of the Clifford hierarchy. So if you want to implement gates from the higher level, then you have to actually go to higher dimensions. In the case of the stabilizer code. Now, okay, this is actually a theorem. So I will prove this theorem, but let me make one comment. That is, well, D-dimensional color code. It has a RD gate, which of course belongs to CD. So in this sense, this topological color code is saturating this upper bound. Okay, now the proof is very simple, and we use a technique which actually used in the previous lecture. That is, so I'm gonna demonstrate a proof in 3 dimensions. No, 2 dimensions. So this is a 2-dimensional lattice. Then what we do is we do this trick. So of course you should imagine like this system is expanding more and more, but just for drawing, I'm just doing this only for them. Okay, now the important fact is that this partition is 3 colorable for all points like object. I put A, and for lines, I put B. And for faces, I put C. Good.
What's script R?
Sorry?
There's a symbol on there which appears to be a script R. What is it?
Oh, this one? Yeah,
Yeah.
just RD gate.
Right, okay, but what is it?
It's the rotation gate that we had earlier. The R sub m with the 1 e to the I 2 pi over 2 to the m.
Right.
So it's a like bunch of square root of t, basically.
Right. Okay.
All right. So yes, we have seen this partitioning, and the point here is that region A. If I look at region A, these are all like bunch of tiny regions like this. And more importantly, of course, we can draw this picture so that this width is thick enough so that there's no stabilizer generators acting simultaneously on different A's, right? So this means that each region, each patch of A is tiny order 1 volume region. But we are assuming that there is no logical operator on order 1 region, which means that GA must be equals to 0. There should be no logical operator. But then now let's look at regions B. Then again, region B is a bunch of collections of disconnected pieces. So, yeah. So again, I can say that ZB is equals to 0. And then finally, ZC is also equals to 0. Now, we have split the system into 3 regions, so 3 subsystems. And, well, so this is M equals to 2 example. So this means that L should be in C2. Yeah, right. Any question? Makes sense? Good, good.
When we were discussing that structure last time, you were talking about like improper Hamiltonians and how like the A regions become like basically sinks for the excitation states. Like this.
Oh, right. So this figure appeared already twice in the past.
Yeah.
The first time it appeared when we discussed the bound on the number of encodable logical qubits. We encountered this object. The second time is we discussed the thermal instability of the toric core, where this A was actually a sort of qubits, the terms in the Hamiltonian, which are lost. Yes.
Yeah. I was just wondering if there's any connection between that and how.
Right, it seems so. Yeah, I do not know why, but this way of thinking appears multiple times. So maybe another fundamental result I'm not gonna discuss in detail is that you can think about this type of partitioning and then assume that the topological entanglement entropy is strictly equals to 0 in a sense that there is no subleading term in the area law. And you can show that actually the whole wave function can be prepared by some local processes. And so it's a trivial quantum state. And then you actually use similar partitioning. So yeah, there must be something, some fundamental reason. Okay, and then one more comment I want to make here is the following. So we split the region into 3 regions, the system into 3 regions. Region A, B, C, so that there's no logical operator. But what if we try to split the region into, like the whole system into 2 regions, trying to prove something like this? But you see that this doesn't work because if you have region A and its complement, it's always equals to 2k. So at least one region should be supporting one logical operator. So in this sense, this partitioning into 3 regions is like minimal you can do. You cannot do better than this. So this, we are coloring ABC. This is basically a trick, very clever trick to have nice partitioning where these 3 regions supports no logical operators. Okay, that's good. So, but this is just 2 dimensions, and then now let's go to 3 dimensions, or in higher dimensions. Then, so in D equals to 3, we want to have some partitioning into A, B, C, D, 4 regions, so that this kind of relations hold. So the question is, how do we find such a partitioning? And so for that, let me tell you how we can obtain such a figure. So for D equals to 2, the way we construct this is the following. We first draw this grid. As I sort of mentioned, implied, A is like point, B is like line, and C is like plane. So what we actually should do is you draw this some grid, 2-dimensional grid, and first we sort of fatten points or 0-dimensional object by So previously the point was like this tiny object, but it now become bigger. So this is the what we mean by fatten points. Then we next fatten edges, by which I mean the following. Okay, like this. If you keep doing, well, then now you get this figure. Right? So basically you start from zero-dimensional object and then make it bigger, then one-dimensional object and then make it thicker. You get this nice figure. So in three spatial dimension, what we should do is we draw a three-dimensional grid. This is approaching the limit of my drawing ability, but what we should do is first we okay, let me just pick up this point, and then first we have this zero-dimensional point. Here you put some sphere. This is sphere. So this is, first we fatten the zero-dimensional object. Then next, we enlarge these lines by putting some tube. Okay. Then finally, we make this plane thicker. Then we call this point as A, H as B, plane C, and the remaining volume D. And then the point here is that this nice partitioning has a property that all the region colored in A are separated, because A used to be a point and then point are separated. B was edges, and then edges was sort of originally connected, but now we have some point sort of expanded. So now because of this point, these edges are now separated. And then you can just repeat this argument and show that this object satisfies properties we are mentioning. So you can show that these four regions suppose no logical operators. As a result, logical gate must belong to C3. Yes, great. Okay. Yeah, so it's kind of very clean proof. Any question for this? It's clear. Yes.
So does it seem to give rise to like the tension that if we have higher dimensions, we can build inherent error correction properties in like dimension 4, but then the cost to implement, let's say, fault tolerance, or to implement fault tolerance with this transversality using transversal gate set becomes more complicated. So it seems like a tension between like if we use higher dimension code, like certain properties are better, but certain properties get worse also.
Oh, some some properties. Right. So right, that's actually very true, and then it's actually, I'm gonna give you exactly one example of such a property that is, it's not quite related to spatial dimensions, but it turns out that if the code, okay, maybe I can just keep doing on that, but this is not a direct answer to your question in the sense of the spatial dimensions, but I think it gives you some sense of this tension between higher level of the gates and the coding properties. So for the purpose of a quantum computation, so these gates from the higher level are very precious resources, but at the same time, the code with higher level gates has a weaker error tolerance. So suppose that, so this is a theorem. So if the code has erasure threshold, in a sense that the loss tolerance, so you lose qubit. So this PL is a number, the probability of qubit loss you can tolerate. So if this number is big, then it's fine. It's very good. And suppose that this is bigger than this number, 1 over n. Then it turns out gates are m-1 level. This is something you can prove. Actually, I was planning to do this, put this as a homework, but I discussed with Daniel, and then we decided we shouldn't have a homework this week, so I'm gonna explain this. But it's a very simple result to prove. So, but let me say that, let's say this PL is a very big number, then this means that then the gates you can do is actually restricted to kind of lower level of the Clifford hierarchy. This is the result. And proof is pretty simple. So this is m qubit region, and you just split it into m regions. And by just picking up qubits randomly. Now, since the code has a loss tolerance rate which is larger than 1 over n, which means that this qubits on A0, so we pick Q0, so qubits on chosen randomly with probability 1 over m. Okay. Now let's ask if A0 can support logical operator or not, and then we claim that this must be equals to 0, because if then losing qubits on A0 with encoded quantum information by losing qubits A0, right? Because basically there is some logical operator which were supported on A0, but these qubits are taken by someone else. This means that this someone else, well, let's say environment, has an access to this information. Now I don't have access. I shouldn't have access to this information. Therefore, the A0 should be equals to 0. But you can repeat this argument for all the region. The AJ equals to 0. This means that L should be inside C n minus 1. So gates from the higher level of, well, it's good, but unfortunately it has a lower error threshold.
When we just started talking about the toric code and we were talking about erasure errors.
Oh, right. So toric code.
Talking about like the percolation threshold and how if P is right at about 0.5,
yes.
then it can still all
Yes, so PL was 0.5 for toric code, which means that, well, so it is saturated in the bound dimension. Yes. And then toric code, actually, you can do a gate from C2, because if you have a pair of the toric code, you can implement C0 or CZ among these two guys. So this actually tells you that, for example, there is no space to write. Maybe I can just write 3D color code. The error threshold must be at most 1/3, because it has the level 3 gate. But I don't know if this 1/3 is the actual number. I don't think so, but at least you can prove that it is the upper bound. Okay, and there are several other kind of applications, especially, so this doesn't assume any geometry, but in these spatial dimensions, and then if you have gates from higher level, actually the upper bound and the code distance is actually smaller, and so the code and the coding property itself becomes worse. This is a kind of interesting trade-off between error tolerance and Clifford hierarchy. Really. Okay, so that's all about this Clifford hierarchy business, and I guess before taking break, any questions?
You know what I'm going to say? I'm still not happy about that decomposition question that I raised however long ago it was.
Sure.
So without that, the counting procedure seems to be all closed.
Counting procedure?
Okay. You're saying that the distinction between these different levels is well defined mathematically. I raised an objection saying that you can decompose some larger gates in terms of some smaller gates.
Yes, so that everyone knows, and so what does it imply?
Right. Well, if you have you say that, okay, this gate here, point to whatever gate, this gate exists in the third level, but does not exist in the second level because the second level isn't big enough. And I say, well, here, Solovey-Kitaev, or whatever decomposition theorem you like, I have now written my gate in terms of 2 cubic gates. What's happened to your counting?
Counting? What does it mean?
Okay, I'm counting dimensions here. I'm counting levels. Right? Now, if any and all 3 cubic gates can be decomposed in terms of gates of weight no more than 2, what does it mean to say that something only exists in level 3? Now, I'm satisfied that the Clifford hierarchy is a thing, because I've seen it referred to all over the place. But in terms of explaining why it's a thing, I'm still completely confused. I can't,
So I understand why you're confused.
I mean, I ask you this question before and you say, oh, it's not a group. I'm not invoking its group properties. I'm invoking the properties of multiplying matrices.
Sure. So can you be more specific about your question? I mean, what you said doesn't...
If you controlled Z-gate, there exists some way of writing that, decomposing it in terms of 2 cubic gates.
Right.
And I don't think you need a T-gate for that one. So
No.
why is that a thing?
Hold on. Why are you talking about T-gate? CCZ gate does not...
One of the things...
So okay, multi-qubit, 3-qubit CCZ gate does not belong to the second level. So you cannot create...
Right, so you're saying that there is no way of writing that as a 2-qubit.
No, I'm not saying anything about 2-qubit gate. The claim is that the 3-qubit control Z gate cannot be... is not inside the second level. It is the third level gate, non-trivial gate. Okay. So that is a statement. And now if you say that, can we decompose this multi-qubit gate, 3-qubit gate, into 2-qubit gates? Yes, it is. But I'm saying like, there is no contradiction between these two statements, because 2-qubit gates contains gates from third level, fourth level, fifth level, sixth level, and so on.
Right, so there exists... I mean, I can see that there is a 1-qubit gate which exists on the third level because that's the T gate.
Third level gate, fourth level gate, fifth level gate that exist. Even for a single qubit, you can go like 1,000 or something.
Okay, well, I'm completely not seeing how this decomposition works. You have the set of all possible unitaries that act on however many qubits, right? Now you slice those up according to some rule about which I am still confused into your various Clifford hierarchies.
So it's just like you can, just for simplicity, you can imagine like single qubit gate. Now assume that you can do only Pauli for the total entry and Clifford for the total entry, and if you add T, some sufficient number of T, you can do the decomposition. Yes, that is true.
Right. So I have Clifford plus T, and that gives me level 3. Now you did, as I recall, answer my question that third level is sufficient for universality. And
if you have many of third level gates, yes.
Right. If you have enough, well, do you need the entire third level? Do you need at least one object in the third level? I think you only need a T gate, yeah? T gate plus Clifford gives you universality.
I mean, sufficient number of them. Right. I mean, number means that just implementing T once is not enough.
No, but you have to have the ability to do it, right? I mean, we're trying to construct codes which will protect from local errors and still allow us to do logical operations so that we can build a fault-tolerant computer. That's why we're asking this question in the first place. So you have that set of rules for decomposition, and now you're telling me that there are things at the fourth level which I cannot decompose to lower level.
I'm not saying that. No one said. No one said that. And I see this definition is. I'm saying that this is a set, not a group. That is the answer. I mean, so let's say like if you take fourth level gate, then the statement is that there is a fourth level gate, well, alpha gate, which is strictly outside of the third level gate. Now this alpha gate, you can decompose it. You could probably, I don't know how, but maybe you can do it, decompose it with a bunch of third level gate. And I'm saying like there is no contradiction.
Okay, well, I don't see why.
Because it is a set. Product of third level gate could be beyond third level.
Right, okay, but if that's the case, why is this a useful construction?
Why not? I mean,
I could write down any construction I like, but it may be completely
So for example, it could be the case that the RM gate is more. So why we want to do this? So the goal of the Solveig-Kitaev theorem and so on is that we want to do the fine-tuned rotations very precisely. And then Solveig-Kitaev is one way of us achieving a very precise rotations. This is another way of doing these precise rotations, right? This is just two different approaches.
Right.
Sure. So you are saying like because we can do it with Solveig-Kitaev theorem, that is true. But we could do the same thing with this higher level gate. That is also true. Right. Then now we need to compare these two results from the perspective of resources and so on. Then these researchers, I think these studies have just begun, and so I don't have any concrete thing to say.
Right. I mean, I've been trying to sharpen this question up to pin it down to yes/no questions. This is a thing about statement about matrix multiplication, because if I'm completely confused about what you're saying, what one does is one constructs explicit examples, and you ping those examples. You say, right, is this true or is this false?
So you are mixing two kind of questions. So first question is, I think, I mean, this decomposition and so on is does this lead to any mathematical inconsistency? And then the answer is no, right? Then the answer is that because this is a set. That's period. And if you ask like what is the point of thinking about Clifford hierarchy, then that's another question. Then you are mixing these two questions back and forth. So it's I think that this discussion is very complicated. But the point is that
whether or not it's well posed.
Sorry.
The question of whether or not a construction is useful is completely dependent on whether or not that construction is well posed.
Sure.
You might have other reasons as well, but a necessary condition for a structure to be useful is that it's well posed.
Sure. So what's the question?
I'm still not seeing why this division into different levels is well defined.
Well,
because I can decompose stuff.
Then the answer is just it is a set. And I mean
that's got to do with it.
I mean, I'm sorry, but this is just, I'm saying like multiplication of third level gate could be outside of the third level. Does this make sense? It is a set.
Right. So your set is not closed, it doesn't obey the group axioms.
Right.
So, well, what use is it then?
So then what's the point? Like, if you have a fourth level gate which admits decomposition in terms of third level gate, then what about this?
Right. I mean, I can construct higher order versions of things arbitrarily or almost arbitrarily. For example, where you take the octonions and you do the Cauchy construction again, and you get something that's a
so you don't need to invoke these things, right?
Right. If it doesn't obey certain axioms, then it stops being useful. Right. This is why nobody tries to understand things that aren't.
Just focus on this Clifford hierarchy.
I'll give you an example for why I think. I mean, you made a claim here, which is a question about whether or not something is well posed. It's got nothing to do with whether or not it's useful. I gave you an example from a different area of mathematics of something that is not well posed and is therefore not useful either.
I mean, sorry, like.
I mean, we are.
But sorry, this is a graduate level course, so I mean, I assume like knowledge of group theory and the set theory and so on, like very basic.
I don't know what a group is. I'm trying to ask what
yes,
motivation is for why we're doing this.
Yeah, so I'm sorry, like all answer I can give is this is a set. Now, this should be answering your question if I understand your question correctly, and you don't need to invoke anything like fancy mathematical jargon to see this. This is as simple as saying like this is a set. Okay.
Well. No.
I mean, I cannot help you to understand this because this is such a basic, so I'm sorry.
Well, I think maybe you don't understand my question.
Yeah, that might be the case. You have to focus on the state of question. So if your question is the fact that the fourth level gate could be decomposed into a bunch of third level gate, then if you ask this, this makes this distinction between different hierarchy ambiguous, then the answer is no.
I mean, I'm happy with the idea that if you can take a bunch of 2 qubit gates and bolt them together and get something that lives on more than 2 qubits.
So
because that's the standard result.
Right.
I don't have a problem with that.
No one has a problem with that. Everyone knows this result, right?
Well, that's, you seem to be assuming that I'm asking a very naive question, and I don't think I am. I really don't think I am.
Yeah, sure. Then can you state the question?
So
you mentioned this fourth level gate and could be decomposition and so on. I thought that was a question you were asking.
There are some interrelated questions, but they're all ultimately.
So now let's do it one by one. So you're happy with this fourth level question? You asked that okay, fourth level gate could be decomposed into a bunch of third level gate. Is it a problem or not? And I said no because it is this fourth level gate, third level gate. This is a set. And then, do you understand this statement or not?
Yeah, I'm okay with that.
Okay, then.
I'm just saying, well, why do we concern ourselves with fourth level gates at all?
Yeah, so that's why I said that you are mixing two questions: mathematical questions and motivation questions. And now the question to your motivation question is the following. Yes, sure, a Solvay-Kitayef theorem says that you can do any gate with high precision by doing these decompositions. That is true. But another possible way to do this tiny rotation, let's say you want to fine-tune and do the fine-tuned rotation 2 pi over 2 to the m, very tiny rotations. And then if you only have T gate and a bunch of Clifford gate, then the cost of doing it could be big. Like you might need to apply lots of T gate, and the T gate is not free, and a very long sequence. Instead, in this, if you have a read mirror code and the higher level read mirror code, then by doing logical action, you can do this fine-tuned rotations just one shot, and then you don't need any sequence. That might be more efficient. So this is another type of the question. If you want to compare these two methods in a more exhaustive way, then I do not know the answer. And then in some regimes, maybe Solvay-Kitayef is better. In some regime, this Clifford hierarchy may be better. And I don't have any sharp answer to this question.
Right, okay, I think I see what you're getting at. So if I want to do a fine, precise rotation, right, I can't just do that on the original target qubit. I need a bunch of extra memory as well to do the control. And depending on how precise that thing is, I need a much larger area of it, and I suppose you can call them ancillas. Part of the control system which allows me that precision. Right? And doing the bookkeeping on just how much extra memory I need to have in order to do the precision rotation that I want is what defines that hierarchy. Is that right?
What is memory?
Well, I mean, if I want to do one of these precision rotation gates that you said, okay.
You take some read mirror code and then do it, right?
Right. So I have my original target qubit that I'm attempting to move. And I now do some joint gates with various other qubits, right, as part of doing the control for that, right, because I need some extra resources.
So, right. So more precisely, if you want to implement this higher level gate precisely, one way of doing it is you start from logical zero state. You can reach logical zero state very precisely by applying Clifford. And then you apply T gate or square root of T or RM gate everywhere in the system transversally. And then this RM gate could have some errors, of course. But this is an error correcting code. So you can error correct it by Clifford operations only, which we assume it's perfect. Well, in reality not, but we assume it's perfect. Then we error correct it. Then we decode it. Decoding is again a Clifford procedure, and then you get the state which are rotated by this RM gate, right? Right. So that's how it works. Right. So basically, magic state distillation.
Right. Okay, I see. It's a statement about resources. Okay.
Okay. So right. So in the second part, I'm going to briefly talk about subsystem code. Actually, I was not planning to discuss subsystem code, but since no one took it as a topic of a final presentation, so I decided to briefly explain it. It's actually what we mean by subsystem code is it's not, well, we don't have any agreed definition of subsystem code. And what I'm going to talk about today is sort of a subclass of the fully general subsystem code, which are based on Pauli operators. But hopefully, this example or this subclass gives you some idea of how to generalize these ideas. So, right, and then, so subsystem code. it's a bit complicated object, and then so let me start by giving you intuition. So imagine we have this ordinary stabilizer code, like the toric code or any stabilizer code. So given a stabilizer code, stabilizer code was defined with respect to stabilizer group S, which are generated by bunch of stabilizer generators, where code word subspace was +1 subspace. Now, very roughly speaking, intuitively, the idea of subsystem code, especially the one based on the Pauli operator, is the following. You can think about the whole Hilbert space of n qubits. So this is n qubit Hilbert space. And we have this stabilized code word space. Now let's assume that so this is a 2 to the k dimensional space, well, where you have a bunch of logical qubits. But suppose that k is actually pretty big. I mean, I'm going to define what they mean by large, but it just assume that there are lots of logical qubits. And then the idea is, let's say we only use some portion of my k logical qubit to store memory, and then I don't care others. So okay. So at the very intuitive level, this is the idea of a subsystem code. So you have a big space of the code word system, code words, and then you only use a part of it. More precisely, the whole Hilbert space can be decomposed into a bunch of eigenvalues, list of eigenvalues, right? Then we are interested in code word subspace, which is, of course, everything is +1, right? But even inside this code word subspace, we make some partitioning, and this partitioning has this tensor product structure. So let me get. So what you should think is that maybe you have, let's say, 5 2 to the 5 dimensional code word space, and then you only use these two as a logical qubit. And these other 3 of them are called gauge qubits. We use this word gauge because, well, we don't care what their states. We don't care, so that's the reason. So in this case, the code word space is partitioned into 3 qubit times 2 qubit in some nice way. So this is the idea of the subsystem code. Yes?
So just like intuitively, why would we even want to do this? It seems like...
Right. So what I'm going to discuss today is I'm going to explain one situation where this idea is beneficial. But it's again a trade-off in a sense that because of this way of thinking, we actually lose a little bit of code properties. And it turns out that when we perform quantum error correction, we need to measure stabilizer operators. In the toric code, it is 4-body, but generically it's very big operators, like 10-body or 20-body or whatever. And one merit of using subsystem code is this measurement of a big, let's say 20-body stabilizer generator could be decomposed into a bunch of fewer body operators. So you only need to measure fewer body operators fault tolerantly, and then that is related to that will come from the fact that these errors actually only affect gauge qubit and doesn't affect logical qubit. So there is some merit of using this at the practical level. But we will see that because of this merit, actually, we lose something, and so we will see that. And why are we doing this? And to some extent, I share this feeling with you. Why are we studying subsystem code? And because I think for a long time, this idea of subsystem code was not like particularly useful, but these days, actually, more recently, it has been found that this is useful for code switching and so on. So it may have some nice applications in fault-tolerant quantum computation. Okay, so this is an intuition, but now let me define it more carefully. And I'm going to list a few equations, and but I think it's better to look at actual examples. So we will soon, right after this, we will look at examples. The subsystem code is defined by an object which is called gauge group. I don't know if it's a good name or not, but that's what people call. It is generated by operator O1, O2, and so on. And OJ, these operators are Pauli operators. Okay? But this may not be commuting. So this commutator, they may not be commuting with each other. So G may be non-abelian. That's a crucial difference. Because okay, now, so for now, this G is just a bunch of operators. Typically, we list all these operators are like physical observables, so you are allowed to access, and all the physically relevant operators. But so far, this is just a list of the operators. Now, given a group, we want to learn about this structure, and then we are going to define stabilizer group. Denoted by S. And then this is a subgroup of G. And it is a center of G. And center is just a technical way of saying that it's a subgroup of an abelian group. So meaning that S can be generated by where? Okay. So we have a bunch of gauge group, and then we look at the subgroup which is commuting with each other. And then of course we want to look at the largest such subgroup. And that is what we mean by center. So if we find just some nice sequence of Pauli operator, which is contained in G, but commuting with all the elements, then that is inside your stabilizer group. And this is a shorthand notation that all the elements in the group commute with this guy. Now, we are going to define code word space by using these stabilizer generators. So PS is just a bunch of things which are stabilized by the stabilizer. Now, of course, this definition reduces to a stabilizer code if G is abelian, which is S equals to G case. But because there are some non-commuting element, this generalization happens. Now, I think this is just too abstract, so let us look at an example before even proceeding. And this is something called Bacon-Shor code. And the Bacon-Shor code gauge group is generated by I haven't defined the Hilbert space, which is bad. You can think about two-dimensional lattice. Where qubits are sitting on vertices, and we are going to put a periodic boundary condition. So this is living on a torus. And gauge group is generated by a bunch of two-body Pauli operators. Okay. So it looks like XX and ZZ. Okay. Now here it's very important that XX only acts on horizontal edges and ZZ acts on vertical edges. And maybe you can think about some Hamiltonian realizations, which is XX and ZZ. Some positive constant. Okay. So now, well, even though I write the Hamiltonian, let's not focus on the Hamiltonian for a while and then just study the code structure. So first, given this, gauge group, we want to find the stabilizer group. It is like a symmetry of the G. So then this is something you can just do by speculation, but one, two, three, four, five. Okay, let me write it down. Right. Okay, this object. And Okay, this object. Now I claim that these are generators of stabilizer group. They are translations. So first, let's check that they commute with G. This is something I guess you can see. This one, this string of X commute with ZZ because ZZ overlap twice. The XX, same, overlapping twice. So this is satisfied. We need to show that this is inside G because S is a subgroup. And you can see that this is inside G because, well, these edges, you can create this operator. So this a bit thick with two string are the stabilizer group. And you see that there are only L stabilizer generators, where L is the length of the lattice generators. But if you multiply all of them, you get an identity, which means that it's actually only L minus 1 are independent. And the same here. Then if you look at these terms very closely, then you would notice that there are no other operators inside this stabilizer group. Alright, so now it's good. So there are only 2 times L minus 1 stabilizers. On the other hand, we have L square qubits. So the code word space is huge, right? Because basically L square minus, it's a very, very big space. I actually started wondering if these are all the stabilizer generators. I do think so, but we're not 100% sure. But the point is that there are not that many. Like this is L squared and this is L.
What if the lattice is asymmetric?
Sorry?
What if the lattice is asymmetric?
Oh, it's not translation invariant or some. Or no. What is it? Asymmetric? Like not like a square lattice?
Yeah, like a n by n to the k lattice, for example.
N by right. Then one of the stabilizer generator is very long and then the other one is very short.
It'll just change from the difference of the area to the difference of the area minus the perimeter is what it roughly becomes, I think.
But this asymmetry of the lattice structure is actually something very crucial in the sense that in the case of the toric code, we saw that there's a string-like object living on the lattice. Well, again, you see that this is like a string, but it's a very rigid string. You cannot deform it, actually. Then this is a very crucial difference. I'm gonna talk about the consequence of this thing, which is like a very sad consequence, but anyway. Okay, so this is like one example, but now I need to probably go back to the more formal thing. So by looking at this Bacon-Shor code, we now know that in order to construct gauge group, we just sort of collect all the terms in the Hamiltonian and then look at the commuting parts of the Hamiltonian terms. and then define the coordinate space so that it is in a +1 eigenstate of these symmetry operators. And let's see. Maybe I can briefly explain this. Now let's take that above Hamiltonian. And then we can look at some ground state space of this Hamiltonian. Then, a priori, we do not know if this ground state space satisfies right. We do not know because in the case of the stabilizer Hamiltonian, in order to minimize the energy, we knew that this must be +1. But in this case of some arbitrary Hamiltonian, which is very difficult to solve, there is no way of minimizing energy very easily. We do not know if it is +1 or -1. Right? In general, if you construct Hamiltonian by picking up all these generators of the gauge group, we actually do not know if the ground state satisfies this condition or not. But for certain subclass of a subsystem code, which is called CSS subsystem code, where CSS means like terms are X only or Z only. There is no mixing or there is no Y term. Then this Hamiltonian or this -H is a matrix with positive entries. Right? I mean, I'm assuming Jx, Jz are positive, so they're putting minus sign, so everything should be positive. And under this situation, you can actually use something called the Perron-Frobenius theorem. I hope I'm spelling it correctly, but this theorem actually says that ground state of H, if you write it nicely, then it's actually, you can decompose it in a way that these guys are all positive. This is something you can prove. And then from this information, actually you can prove that ground state space of the this above Hamiltonian is contained in the code word subspace. So you can just safely use that Hamiltonian and look up the ground state space, and you can use it as a code, which is contained in the code word space of the subsystem code. Although we don't know how this gauge qubit is behaving, and so, but this is just a minor comment. Now, having defined the code, we should talk about logical operators. And because of this kind of a complicated structure of a subsystem code, having gauge qubit and logical qubit, definition of logical operator for a subsystem code becomes a bit non-trivial. And it turns out there are two types of logical operator, which are called bare and dressed logical operator. And when I say logical operators here, I mean just Pauli operators, just for simplicity of the discussion. And let me start with a bare logical operator. So this bare logical operator, let's say L, this thing should commute with all the elements in G, but acts non-trivially on the code word subspace, logical qubit. So it has the following structure. If you have gauge qubit, if you have logical qubit, then it can be written in this way. Okay. So it only talks to logical qubit and then doesn't do anything for gauge qubit. And that's because it commutes with all the gauge generators. Now, right. Now, let me further give you intuition by actually looking at the bare logical operator for the Bacon shortcode. This means that we want to find an operator which commute with all the terms in the Hamiltonian, sort of. And one example is the string of X. And string of these. Okay. Now you see that this commute with all the terms in the Hamiltonian because, for example, two-body is easy operator on vertical axis, overlap is 2x. So these are the operators, and then they anti-commute, right? Okay. So anti-commutation. So it's like a Pauli X and Pauli Z operators for my logical qubit. So this implies that the Hamiltonian in that model is at least two-fold degenerate. And it turns out yes, in the sense that the ground state, actually there are only two ground states in this Hamiltonian. But anyway, so this is the bare logical operators. Now, then the definition of dressed logical operator could be kind of obvious because we want to get rid of this identity here. Let me add hat for dressed operators. And the definition of dressed operator is that it commutes with S operator. S means stabilizers. So L is operator which keeps you inside the code word space. But it could act non-trivially on the gauge qubits. So hat yeah, something like this. And now we can look at example of a logical dressed operator. So of course, bare logical operator is a dressed logical operator, sure, but we can sort of deform it. So the point is that anything which commute with S is a dressed logical operator. So you can deform it by adding some gauge generators. So in this case, I applied two-body XX here, and then deformed that string operator. And you have this kind of deformed string. Then this is again what is it? Dressed logical operator. Then you can see that this commute with this Z-type stabilizer. And
Would it not be L hat and S?
yes, thank you. So this is something we can put in. So then you may think that this dressed logical operator is just like a deformed string, but it's actually not, because I keep breaking jokes. But because just by adding this two-body X operator, you can move this X operator anywhere on the lattice. So you could put it here, put this guy here, put this guy here, put this guy here. Right? So the only important thing is that there is only one X operator on each row. Only one Z operator on each column. That is the property of the dressed logical operator. So they do look very different from each other. So for example, let me call this L hat, and then this is R hat. Then previously in the bare logical operator case, this L and the R operator, these strings anti-commuted with each other. But these dressed logical operator, do they commute with each other? Then it is the answer is not necessary. The reason is the action on the logical qubit would anti-commute, sort of, it like X and Z. But the action on the gauge qubit could anti-commute too. Then you get cancellation, and then it's possible that these things can commute with each other. Okay. So now why we want to think about dressed logical operator and a bare logical operator is because when we encode information coherently into the code word space, we want to use logical operators, these bare logical operators. And when we read off information, these are the operators which strictly talks to this logical qubits. But from the perspective of the environment, not noises, it's actually, if you can apply one of this dressed logical operator, that is enough to contaminate logical qubit, right? So when you think about noises, actually you need to look at dressed logical operators. Okay, and so let me briefly just summarize the kind of algebraic structure of the subsystem code. So you have a bunch of stabilizer operators. Okay, then they are commuting. And then now you have logical operators for gauge qubits, and you have logical operator for a logical qubit. Okay. So this is stabilizer group. And here, this picture is like sort of it's similar to Pauli operators in a sense like it's like x and zx, zx. It says that operators on the different column commute with each other. Only in the same column, they anti-commute. So S1, S2, and so on are stabilizer group. And this is a gauge qubit. So it's a logical operator for gauge qubits. And this is the actual logical qubits. Okay. And the gauge operator can be chosen in the way that this is a gauge group. Okay. So this is S, and then this is J. Okay. So I guess this picture is sort of nice because if you have bare logical operator which acts only on logical qubit, these guys, this bare logical operator should commute with gauge group. So it should come in the column which are outside of the this gauge group. So that's here. I mean, stabilizer group could be okay, but stabilizer group is like identity operator. So we don't care. So this is the bare logical operator. And then the rest logical operator commute with all the stabilizer group. So that's basically this entire object. So this big coordinate space. This is the rest logical operator. And what else I should say about this? Yeah, so hopefully this is clear. Okay. Now I'm not gonna give you a proof, but it turns out in the stabilizer code we had this nice duality relations, and it turns out you need to modify things in the following way, where this counts there, and then this counts the rest. And still similar relation holds. Which is actually pretty easy to prove, but from this kind of algebraic structures. But okay, so that's the kind of summary of the subsystem calls. Yes?
Yeah, I still don't understand this picture with the gauge qubit and the logical qubits. Oh,
right.
Well, these two rectangles. Well, what do they represent again?
Rectangles represent Pauli operators.
So small white rectangles represent
yes,
Pauli
yes,
operators.
yes. And then, right, so there should be n of them.
What's n?
N is the total number of qubits.
Okay, so this is for...
Right, so there is like n qubits in total, and then you pick some of the subspace of the Hilbert space by putting these stabilizer generators, S1, S2, and so on. These are Pauli operators. So in our example, it's this X and this Z operators. Okay. Then now our Hilbert space is, the code word space is defined in a way that it commutes with this S operators. Then I'm putting all the logical operators here. So to say that this is commuting with these stabilizer generators. So maybe I shouldn't have started with this figure, but maybe started with this one. This is just a list of all the independent Pauli operators. Maybe I could. The boxes. Now let me think about the most trivial case, that is stabilizer generators, a bunch of Z operators. Then these basically fix my qubits to be 0 state on 1 and 0 state on 2 and so on. Then my gauge qubit is and so on, and the logical qubit. I mean, yeah. So in this example, we are looking at a situation where a bunch of qubits and these qubits are used as logical qubit, and these qubits as a gauge qubits. Then these are just qubits killed by stabilizers. Okay. And basically, you can just transform this object into that object by applying some Clifford gate.
I guess I'm just confused about, so those qubits aren't like physical qubits though, right?
So here it's a physical qubit.
So
Then here it's not. It's not. It's just an algebraic structure.
Right, that's what I thought we were including. But on this picture...
On this picture, it's just, well, maybe I shouldn't have drawn this one. So first of all, they have the same commutation relations. Algebraically, they are just the same.
Yeah.
Now, you can just apply some big Clifford operator. And you can basically convert this object into that object in a way that, well, S1 is like U, Z1, and so on. And this U, the Clifford operator, is a kind of a encoding circuit of your subsystem code. That's how you can think about it.
So when you mean by logical qubits there, you, on just a label, the orange box, you mean like logical qubit operators, right?
Right, operators. And these logical qubit operator can be obtained by conjugating Z on these qubit with. So, right. So I think, sorry, this is a mess. We put O0 here, and then these are gauge qubit, and then you can do anything, and then logical qubit. Then we think of putting big U Clifford. This is an encoding circuit, and then outputs the code word. And then after this output, it turns out that the stabilizers and so on, logical operator for gauge qubits and logical operator for logical qubits can be organized in this way. Right. Okay, so this is the subsystem code. Now, why is it useful or why is it bad? First of all, why it's useful can be seen from the following observations. In order to do error correction, we need to measure stabilizer generators. But this is a very big object. It's a 2L body, XXXX. it's very difficult to measure, and then at each step there may be some errors, and then, it's very difficult to measure. But it turns out that this measurement can be done can be decomposed into a bunch of 2-qubit measurement. So what we do is we measure this horizontal two-body X operators separately, and then that should be enough, because the point is that this X operator is in the gauge group. So measuring this could affect gauge qubit, but it shouldn't affect logical qubit, because this XX commute with the bare logical operators. So this is nice, because in order to measure the very, very big stabilizer generators, actually you really don't need to measure 2 L-body operators, but you can just measure only a 2-qubit measurement, and then that's something you can do with high precision. And then you just correct these results, and by correct means that you just multiply all these results of plus minus 1, and then multiply them, and then that's your result of the syndrome measurement. So for this reason, you can decompose this measurement into smaller pieces, and this is very beneficial. That is the merit. And then because of this non-commutativity in the gauge generators, actually you can generically decompose the. It is often the case that if you have high weight stabilizer generators, you can sort of construct a subsystem version of the stabilizer code, where the small gauge generator can add up to a stabilizer generators. That is the case. So that is a merit. But unfortunately, because there is a price we need to pay, and then that's something we are going to briefly look at. And so the claim is the following. This Bacon-Shaw code is actually not that useful, in a sense that its erasure error threshold is actually 0, or it's some p which goes to 0 as n goes to infinity. It's not that useful. And to see this, actually, let's assume that we lose qubit with this probability, loss probability. Then let's take p to be a very, very small number, like 1% or something. But we assume that this L is big, and then we are interested in the regime where L becomes very, very big. I mean, we are considering a family of codes. Now, no matter how p is small, if L is big, then if we look at, let's say, this horizontal line, then there should be around p times L qubits missing, right? I mean, if p is very small, we just need to take L very big. So that implies that at least there should be 1 or 2 maybe, but at least 1 missing qubits in this system with very, very, very high probability. You can do the same thing, like you can find at least 1 missing qubit, 1 missing qubits from here, 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 and so on. do this very easily from each horizontal lines. All right. Then why is this problem? Because we have seen that the bare logical operators, dressed logical operators, you can sort of shift the location of X operators. Now, then you can easily find some dressed logical operator defined in this way. So you can easily actually contaminate on the qubits with this dressed logical operators, right? So this actually implies that the environment can carry your logical information. So therefore, erasure threshold is you need to take P to be very, very small, or P needs to be as small as 1/n. So for this reason, this code doesn't have an error threshold. And another kind of complementary way of understanding this is that if you have a bare logical operator, which are more important when we talk about encoding and decoding. So that this is a string-like object going in up direction or horizontal direction. So if you look at this horizontal axis, then again from this argument, there must be at least one missing qubit. So you really cannot define a full bare logical operator on any vertical lines. This means that there is no way of recovering this logical qubit information. I mean, you could, of course, measure a dressed logical operator, but that point is that information contains this junk from gauge. Then we are not interested in the state of the gauge qubits. For this reason, there is no way of fault-tolerant. Well, there is no way of retrieving the information back from the Bacon-Shor code. So this is like kind of a truth you need to face because it's the price we need to pay from the fact that we can decompose this big stabilizer generator into these smaller pieces. Now, well, here is just my own comment on this physics. So for this reason, I was not interested in this Bacon-Shor code or subsystem codes for a long time. But more recently, it has been found that this subsystem code is a very nice, could be a very nice architecture for fault-tolerant quantum computing. So there is actually a thing called a three-dimensional gauge color code, which is a generalization of the color code in 3 spatial dimensions. And this gauge color code is very nice because this this subsystem code, it is a subsystem code in 3 spatial dimensions. This code word contains both 2-dimensional color code and 3-dimensional color code. And the 2-dimensional color code, you can do a Clifford transversally, but you cannot do anything else. In 3D color code, you can do T-gate. So this subsystem code contains 2 stabilizer code as like a subclass, where if you combine them together, then you can perform a universal set of gates. And then the trick is that you actually need to switch between these 2 different codes, somehow fault-tolerantly. And then it has been recently shown that this procedure can be done fault-tolerantly by some nice trick. So for this reason, this subsystem code may have some practically useful with having some nice fault-tolerant properties. So I said that the Bacon-Shor code does not have an erasure threshold, but it doesn't mean that all the subsystem code does not have a erasure threshold. There are some nice code which have erasure threshold and very high and nice nice noise threshold and so on. And these systems may be useful for applications. Yes.
Just a comment about the 3D gauge color code. But it seems like this is interesting because the stabilizer can encode both the 2D and the 3D. But I mean, do you need this to be a gauge color code? So I'm just saying, it seems like subsystem code is that we just adhere additional qubits and then we treat them as if they're gauge qubits, and therefore we can get away with lower weight measurement operators.
So right.
But that doesn't seem like it relates to the property of having the.
Okay. Right. So this 3D gauge color code. So this 3D gauge color code, I said it contains 2D color code and 3D color code, but in the following way. There is a choice of gauge qubit, or separation of gauge qubit and logical qubit, so that you have 2D color code. Or there is another kind of a choice where you get 3D color code. And then for that, you need to do different way of partitioning of gauge qubit and logical qubit. Then this partitioning is kind of non-trivial. Then you need some non-trivial quantum operation to switch between them. So once you can do this switching, you can use good property from 2D color code, and then you can use good property from 3D color code. But by just having gauge color code itself, you need to further specify which what is your logical qubits and so on. And that process is something missing.
So in that regard, can we say that the more useful part of the subsystem code is the fact that because we have additional gauge qubits, we have the freedom to choose which one is our logical qubits, which allows for the possibility of having multiple codes in your stabilizer.
Right. Now, we can choose, but I mean, we cannot just say like, yes, I want to use this, but we actually need to make sure that so we basically need to fix which gauge qubits so the state of the gauge qubits should be kind of fixed. And then, so these procedures are actually not that trivial. So this is basically the procedure of picking either 2D color code or 3D color code. And then this process can be done by some error correction, in the sense that you measure the operators which you hope to turn into stabilizer generators, and the error corrected. Then that's how it works. And so in principle, by doing this, you can do universal gate set, but no one knows about the cost of doing it. I mean, magic state distillation is a very nice framework, and but we know that it costs a lot. And actually, I heard from Alex Kubica that he sort of studied the resource requirement of this 3D gauge color code, and then he mentioned that it's actually 3D gauge color code. It's even worse than the magic state distillation, and I'm not so sure about this. I don't know the detail, and he just said this to me. But I have a feeling that no one has, paid serious attention, put serious effort into this kind of 3D gauge color code and this subsystem code. And then on the other hand, many people have thought about magic state distillation very seriously. So I feel like this is the just like a lack of our efforts. And then also, of course, magic state distillation relies on a code where we can implement a T-gate transversally. So I feel like intrinsically these two methods have the same difficulty. So I think I feel like this method and the magic state distillation should be as bad as the other one.
Okay.
Or as good as, it depends. But I'm personally more interested in this subsystem code and 3D gauge color code just as a model of topological order. And that's a very interesting systems. And yeah. Anyway, so that's it. Yeah, I think that's it. So if you have any questions, please ask me. Okay, if not, let's finish.